Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to better understand and remediate DoD sites impacted by PFAS. We'll start off with Mr. Thomas Wanzek from Oregon State University, who will discuss his doctoral research on the persistence of PFAS source zones in areas of historical AFFF usage. Tom's presentation will be followed by a brief Q&A session. Then Dr. David Reynolds from Geosyntac Consultants will present research results from a recent pilot test of In-Situ Foam Fractionation to remove PFAS mass in source zones. Dave's talk will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A session featuring both our speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you have difficulties viewing the slides or if your screen freezes, try keying in Control and F5 to perform a hard refresh. And if you're accessing the audio through your computer, just click the arrow next to the Join Audio button, select the speaker and microphone, and follow the prompts as they appear on your screen. If you continue to have technical challenges, please call into the conference line shown on this slide. You may also submit a comment using the chat box in Zoom. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for our two speakers. And in case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Note that we will also be live streaming the webinar on the SERDP and ESTCP YouTube channel, so that's another option for joining today's proceeding, and the link is also shown at the bottom of this slide. Just a few reminders, today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. Please do not wait until the Q&A period to submit your questions. We do encourage you to get them in well in advance of the Q&A sessions. And when submitting your questions, please add your organization name at the end so that we can identify it during the Q&A. The next few slides will provide a quick overview of the SERDP and ESTCP programs. SERDP is the Strategic Environmental Research and Development Program, which was established in 1991 by Congress as a partnership between the DoD, the DOE, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demos is the ultimate transition to implementation and regulatory acceptance. Note that SERDP and ESTCP are complementary programs, with much of the SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demos are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are several environmental drivers for the type of work funded by SERDP and ESTCP, with the underlining objective of sustaining DoD ranges, facilities, and operations. This, as you can imagine, is a broad undertaking. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munitions constituents, as well as other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, and developing management approaches for contaminants of emerging concern. The second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations on DoD installations. We have several main focus areas for research and development at SERDP and ESTCP, and those are shown here. And as you can see, the first one is PFAS and AFFF, and that's the subject matter of today's webinar. I'd like to point to your attention to the broad range of PFAS-related projects that are being funded by SERDP and ESTCP. You can access an overview of our PFAS program as well as project descriptions using a link shown here and shown also in the chat box that was just disseminated, the chat that was just disseminated. Note that the boxes along the top of the graph illustrate workshops that have been held to develop a strategic plan for addressing PFAS issues, with the latest workshop just occurred this past summer in Chicago. A summary report is available for each of the workshops. The 2022 workshop report should be available in the late fall, so please make sure to check the PFAS webpage to download a copy of those proceedings. Each SERDP project at the top part of this graph has an associated box with a title, which links to full descriptions of each project, as well as any specific reports published as part of that project. And for each ESTCP topic listed, those represent single topics, and you can click on the project title to go to each of the respective project web pages. As we mentioned earlier, technology transfer is very important within the SERDP and ESTCP programs. Technology transfer efforts include the development of videos, training workshops, and guidance documents. The webinar series is a substantial component of our technology transfer efforts. With the webinar series, highlighting research and demonstration efforts from all of our program areas, not just environmental restoration. So as you can see, upcoming topics include an overview of water resilience projects late August. There's 2 AFFF related webinars in September. And then later in the year, we've got topics such as the use of environmental DNA to monitor population parameters on DoD lands, and the detection and characterization of buried ordnance in marine environments. Registration is open for webinars throughout the year, and we expect to finalize and post the 2023 webinar calendar shortly. You can find additional information about upcoming webinars at this link. Note that in addition to upcoming webinars, you can access past webinars on this link. They are all archived and available for viewing via video or via downloading the slides. In closing, please save the date for the 2022 SERDP and ESTCP Symposium, which will be held in person in late November and early December in Arlington, Virginia. This event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. And before I turn it over to today's speakers, I'd like to remind you that a copy of the presentation of today's session can be downloaded now from our webinar webpage. The link is in the chat box. And we would appreciate it if at the end of the webinar, you can take a moment to complete the survey that will pop up, because it does help us with planning purposes. It is now my pleasure to introduce our first speaker, Mr. Tom Wanzek, who is a doctoral candidate in the Department of Crop and Soil Science at Oregon State University. Tom is advised by Dr. Jennifer Field and Dr. Marcus Kleber. His doctoral research focuses on system-scale soil properties and PFAS molecular parameters related to PFAS sorption in AFFF impacted soils. And prior to starting his doctorate, Tom had the opportunity to be involved in environmental remediation and nutrient cycling projects as a researcher at the U.S. Department of Agriculture. He received his master's degree in soil science also from Oregon State University, and we're extremely pleased to have him today. Tom, please proceed.
Thank you for the introduction, Rula, and good morning, everyone, or good afternoon to some of you. Today, I'm going to talk about some of the research that I've been involved with here at Oregon State, and then also some research that's been conducted by our collaborators, Konstantinos Kostarelos and Chris Higgins at Colorado School of Mines. There we go. So just to go over an outline for the presentation today, talk briefly about aqueous film forming foam and their source zones, go over our project objectives, talk through some of the mechanisms that we've been working on in terms of PFAS interactions with soil and sediments, talk about PFAS interactions or potential interactions with non-aqueous phase liquids, go over some of the work we've been doing on unsaturated PFAS transport, and finally move on to some conclusions and potential benefits to the DoD and constituents. So briefly, AFFF source zones arise from repeated applications of aqueous film forming foam to different locations. And these aqueous film forming foams can carry high concentrations of fluorinated PFAS. And this PFAS mass can be retained in significant proportions in the soils underlying these application sites. And there's mounting evidence that organic carbon alone does not explain all of the PFAS has been retained in these different locations. And so understanding the mechanisms of retention is vital and, for predicting the mass that may be retained at future sites, but also understanding what's happening at legacy sites. Another issue that we need to contend with is that in these AFFF source zones or firefighter training areas, PFAS and AFFF are common co-discharged or co-disposed with other types of liquids, one of them being non-aqueous phase LNAPL, and specifically here we're thinking of different types of fuels. And interactions between these LNAPLs and AFFF is largely unknown. Finally, we need to move into characterizing the actual media, the soil media that underlies these source zones, and PFAS retention at the air-water interface and the soil-water interface, so under unsaturated and saturated conditions, can be significant. And transport under these different conditions can require significant measurements and different modeling efforts. So for example, down here at the bottom of the screen on the left-hand panel, we see what might be a semi-tortuous pathway for a PFAS molecule under saturated conditions, with the aqueous phase being in dark blue, and we're mostly looking at mobile water here. On the right-hand panel, zoomed in a little bit, is a representation of what the system might look like under unsaturated conditions, and we see that red line, or the tortuous pathway, is much more complicated and is following mobile and immobile pockets of water. So having an understanding of the processes that go on under these two different systems is very important for predicting what's going to happen with PFAS molecules. So the objectives of our grant, our overview of our research, the first objective was to identify mechanisms of interaction with organic matter and mineral phases under saturated conditions. The second objective was to determine what, if any, phases may form when NAPL and AFFF are mixed or co-disposed, and how that may affect PFAS transport. And finally, our third objective was to consider PFAS transport and sorption under unsaturated conditions. A brief overview of the history of mechanisms of interaction. For the majority of PFAS research over the last 20 years or so, research has used mainly analytical grade standards at semi-low concentrations. Majority of studies have been conducted using batch equilibrium studies, and the handful of column studies that have been used aren't entirely representative of what may be going on in the natural environment. And one of the major conclusions is that the equilibrium soil partitioning coefficient is the predominant variable that describes what's going on here. And that variable is related to the affinity of PFAS for organic carbon in the system and the amount of organic carbon that's present. One of the underlying assumptions or background on this KD paradigm is that it was originally developed and used to predict the fate and transport of non-ionic contaminants. Even still, it has been applied to PFAS research, even though PFAS are or can be under environmental conditions ionic compounds. For example, there's a mounting body of evidence, like we mentioned, that the organic carbon content alone does not predict PFAS partitioning to soil. And there was an EPA study that came out just about a year ago showing that there's a significant amount of variability in KD values that have been measured both in the field and the lab, and that relying on that value alone may not be entirely advised. And so one of the needs that we identified was that an approach needs to be developed around an approach to predict partitioning, or at least understand mechanisms of partitioning to soil and sediment, needs to be developed around ionizable organic contaminants that goes beyond, but also incorporates the KD approach. And so to do that, we designed some experiments that use PFAS that were delivered in a complex, complete AFFF. We were working under a few different sets of concentrations, but focusing mainly on the higher concentrations, which are common to PFAS source zones. And we were also did our best to design these experiments using realistic environmentally relevant conditions. So beginning with our saturated experiments, we collected 4 soil horizons from a site that was known to support long-term AFFF source zones. We applied a dilute AFFF, so it was diluted below the application rate, and that was done to avoid the presence of micelles and to focus solely on PFAS soil interactions. Some results from these experiments. Down at the bottom of your screen, you see 12 breakthrough curves for 3 representative PFAS, with the number of pore volumes flowed on the x-axis and the concentration over the original concentration on the y-axis. One of the things that we observe here is that for these different soil horizons and different systems, breakthrough is not consistent as a function of PFAS, the PFAS analyte, and is also not consistent in terms of horizon order. And what we took away from this was that the KD model, at least an equilibrium-based model, may not be applicable to all of our PFAS that were delivered in the AFFF. And through these experiments, we tracked 34 different PFAS. And the KD model may not be applicable either due to PFAS loss, which we see here, for example, under the PFOS, so C8 sulfonate PFAS, where the C over C naught curves stay very low. There's significant tailing, indicating mass loss to the column. And we concluded that based off of these results, additional parameters may be required, to also incorporating KD, and that partitioning to the organic carbon is likely not the only mechanism active for all PFAS. And so to further explore what variables might be acting, we used a polyparameter structure, quantitative structure property relationship approach to describe mass retained. And we were able to come away with a model that incorporated 3 easily measurable soil chemical and physical properties, which were down selected from a set of 9. We also incorporated 3 PFAS parameters that were down selected from a set of 14. And we see that model presented here at the bottom of the slide. Each of these parameters allowed us to make mechanistic inferences about what might be going on, or the different parameters that may be controlling PFAS absorption or related to PFAS absorption in the soil. The PFAS properties, are highlighted in green. So we have the molar mass of the molecule, the mass of fluorine on the molecule, and the number of nitrogens that are included in the PFAS structure. The soil properties are indicated in blue. We have the amount of oxalate extractable iron oxide, the percentage of organic carbon, and finally, the specific surface area measured by the N2BET measurement. And one thing to point out here is that we see in the Z parameter that the surface area is related to both the mass retained of anionic PFAS and zwitterionic PFAS. So the anionic PFAS do not contain nitrogens, and the zwitterionic PFAS, in our cases, do contain nitrogens. And the iron oxide content and the organic carbon content were only related, at least on a statistical basis, to the PFAS that contained nitrogens. And we wanted to build our confidence in this model. So we did a set of internal model validation exercises and also some external model validation. First, on the left-hand panel, we see the internal model validation. We have the predicted mass retained on the y-axis plotted as a function of the measured mass retained. So the predicted mass retained from the model and the amount that we measured in our column experiments. And all these data points are organized as a function of the different soil horizons involved, excuse me, in the experiments. One of our first takeaways is that we did not see groupings of the horizons, which indicates that the different soil horizons were not, one soil horizon over another was not driving the model compared to another. And we also calculated an R-squared value of 0.84, which was significant, and a root mean squared error of 16.2 to give us a metric to compare external model validation exercises. On the right-hand panel, the graph is oriented in the same way. Here we plotted, or we applied the model to some external control sand columns that we also conducted, and we see a comparable RMSE of 17.8 versus 16.2, which gave us some confidence that the model was functioning well. So moving on, we repeated a set of similar experiments, but this time, so the same setup, same soil, but this time we used AFFF, the applications at application strength, so 3% where there are micelles present. On the figure on the left, same orientation as before. When we apply the model to this data set, we see that the model is actually under-predicting what we are measuring in the system, and it seemed to be doing it in a relatively uniform fashion. And so what we were able to do is we're able to isolate the contribution of micelles to the retention of PFAS. And after adding this parameter, this additional CMC parameter, we found that the presence of micelles can increase the PFAS mass retained on the soil columns by an average of 27%. And to wrap this section up, we found that the KD model was appropriate for some anionic short chain PFAS from some of the soil columns. We also found that we were able to build a PPQ-SPR model to describe PFAS mass retained for all the PFAS in our AFFF, and that model was able to highlight some of the mechanistic underpinnings that may be driving PFAS retention in these soil columns. And specifically, one of the big takeaways that we weren't expecting was that hydrophobic exclusion from the aqueous phase to any available surface seemed to be one of the key parameters driving PFAS mass retention. And then finally, micelles. The presence of micelles can significantly increase the PFAS mass retained in a soil system. Moving on to PFAS interactions with NAPL phases. During a literature review, we weren't able to find a significant body of literature that considered PFAS interaction or AFFF interaction with LNAPLs. And so first we conducted some batch tests to see what would happen, illustrated down here in the figure on the right. And when looking at this figure, the takeaway from here is that the gel phase, or there did appear to be interaction between the AFFF and the LNAPL, and that's highlighted by this iridescent gel phase. We were able to identify the type of gel phase that was formed as a Windsor type 2, and that led us to conclude that jet fuel A, or jet A, can be a significant sink for PFAS, and that this gel may be highly immobile in soil and sediment systems. To that end, we conducted a set of column experiments where we introduced residual NAPL into a sand column. And first, we applied a constant flow of AFFF to that column. And as you see down here on the left-hand panel, the number of pore volumes flowed or produced on the x-axis and the concentration of the concentration not on the y-axis for a set of example PFAS from this AFFF. And what we observed was insignificant breakthrough of the PFAS, and over time there was a significant increase in pressure, indicating that there was a gel forming or some sort of pore clogging going on, and we see that pressure increase here on the dotted red line, and we maxed out around 100 to 120 psi before we had to shut down the experiment for fear of destroying our experimental setup. As a follow-up experiment, we conducted a constant pressure experiment where we set the flow rate such that a pressure could be maintained over time. And the big takeaway here was that, again, we saw insignificant breakthrough. For example, here we're looking at PFAS breakthrough. But what we did see was that over time, flow, or the volume produced from the column, dropped to near zero, indicating that pores were being clogged by something. And on analysis of what little volume did break through, we found that 79% of the PFAS mass that was applied was retained in the column, likely largely in the LNAPL phase. And to that end, we're moving forward and building a LNAPL repertoire, for field collected LNAPL repertoire, and are analyzing those LNAPL samples for different PFAS contents. There are many PFAS present, such as anionic PFAS, PFAS, PFOA, everyone's favorites, but also several zwitterionic PFAS and neutral PFAS. And after these analyses, we're finding that LNAPL may be a long-term source of PFAS in source zones. Finally, moving on to our unsaturated transport experiments. When considering unsaturated transport in physical media, it can be a very complicated topic, especially as the system moves to higher degrees of unsaturated to water unsaturation. And so the first thing that we determined that we needed was a model or an approach that allowed us to better understand the physical transport of contaminants through unsaturated systems. To that end, we developed what we're calling a mass transfer index, which takes unsaturated transport and simplifies the modeling and measurements needed down to only needing to consider one variable, this T parameter here. The importance here is that with this simplified model, it allows for a broader applicability and use. We then conducted similar quasi-saturated experiments to measure PFAS absorption at the air-water interface, or rather to measure the air-water interface partitioning coefficient, or KIA. And we conducted these experiments using relatively ideal media, so very round sand media with residual air entrained in the column. And we see down here in the figure on the right, pore volumes plotted on the X, concentration of PFAS plotted on the Y. We observe that the data points here in blue circles, they had a sharp arrival front, they dropped faster than we were expecting, and there was also a significantly long tail. And we found that this data was not well fit by either an equilibrium Langmuir model, but was better fit by an equilibrium Freundlich model. To further understand what is happening to PFAS partitioning at the air-water interface, we were able to collect some AFFF impacted groundwater and conducted a series of column experiments to measure the KIA of these different classes of PFAS, highlighted over here on the right, at the air-water interface. And what we're able to do with this set of experiments is that we were able to develop a second PPQSPR model that describes PFAS retention at the air-water interface, or log 10 KIA. And we see that model shown down here at the bottom of the screen. The variables that were included were the longest fluorinated chain of the PFAS, the C18 retention time on an liquid chromatography setup, and then also the amount of concentration that was going into the system. And one of the things that we were able to take away from this was that this was a PPQSPR model that could predict the air-water interface partitioning coefficient of several different classes of PFAS, but that also could be adjusted for the ionic strength of the background matrix and took into account the molecular structure of the PFAS. And we were able to validate these KIA estimates with multiple data sets. And finally, considering unsaturated transport, we moved to another set of column experiments, where this time we were working under highly non-ideal conditions, looking at PFAS partitioning at the air-water interface. And what we found was that there was a decrease in the KIA apparent, or the equilibrium KIA, as flow velocity increased and the concentration of PFAS decreased. And what we see over here on the panel on the right, highlighted in blue, were the data points from the previous experiments that we discussed. And then the data points in purple are from these two sets of experiments. And when the conditions move from relatively ideal to non-ideal conditions, we see that a Langmuir model can significantly underpredict what's going on, and that a combination Freundlich-Langmuir isotherm is more appropriate for considering PFAS partitioning at the air-water interface across a very diverse set of conditions. And with that, I would like to move through a few of our conclusions or main points, and that we were able to show and found that AFFF, when it interacts with LNAPL, can form gels in situ, and that these gels may be a significant source of PFAS in the subsurface. We also found that PFAS under saturated conditions were significantly retained in soils, and they were greater than we were able to predict with the traditional KD equals KOC FOC model. Finally, we were able to develop a polyparameter model that at least gave us a mechanistic insight into the key parameters that may be driving PFAS absorption at the soil-water interface. And we were also able to develop a similar PPQ-SPR model that highlighted the ability of the air-water interface to absorb PFAS under varying conditions. And with that, go briefly over the benefits of the DoD. Again, we were able to identify that LNAPL could be a potential long-term source of PFAS, and that impounded NAPL or residual NAPL in soil systems may require separate treatment from traditional methods. And with that, I would like to say thank you. And there are a few additional resources listed here. And I guess one more slide, move to any questions.
Great, thank you so much, Tom. And as a reminder for all of you, you may submit your questions by using the Q&A box on your screen. We've received a number of questions for you, Tom, so I'm going to start off with one from the Alabama Department of Environmental Management. Can you provide additional details on the soil types that you used in the NAPL column studies? Was it homogeneous soil, or was it clay-based, or what can you tell us about the soil type?
That's a good question. The soils that were used both in the first round of column experiments and also the LNAPL column experiments were highly sandy soils, very low organic carbon, low clay content. And when we initially considered these soils, they didn't present any obvious retention mechanisms, which was quite interesting to us.
Great. And a related question, how applicable is the saturated PPQ-SPR to other soil types and other locations?
Yeah. So to begin to answer that question, the saturated PPQ-SPR model is, from a soil contamination point of view, a best case scenario, because we were working with soils that had very low organic carbon content, very low clay content. The amount of PFAS retention to these soils was on the lower side. To that end, we have also determined the soil type that we were working in, and we've started cross-referencing that soil type with other soils that underlie other known locations, either locations with known PFAS contamination, or other locations where there may be significant PFAS contamination in the future. And we found that a significant number of sites have very similar soils to the one that we were working with.
Great, thank you for that thorough response. Do the parameters included in the saturated PPQ-SPR covary? And if so, were those variables excluded in your study?
We did test for covariance of those of the included variables, and ones that were significantly interrelated we did not include in the model.
Thank you. Here's a question from the Florida Department of Environmental Protection. Are the LNAPL PFAS gels visibly identifiable in the soil? Staining, smearing, discoloring? Did you observe any of that in the gels?
That is one of the questions that we're asking as well. Based off of our initial experiments, we were not able to visually identify any of these entrained gels, mostly because they were formed under systems with residual NAPL. So we're talking very thin layers of NAPL that may be absorbed to the soil. It may be possible, as you saw in one of those figures, that if there was a significant amount of NAPL in the system, that you could visibly identify one, but we have not been able to yet. Great,
thank you. Here's a question from Defense Innovation Unit. Do you know of any companies that are utilizing these processes at scale to remove PFAS? Are you aware of any sort of applications utilizing some of the basics and fundamentals that you described today, Tom?
Not sure if they'll be able to answer a follow-up question, but are we talking remediation technologies, or are we discussing remediation of the LNAPL?
More generically, processes at scale targeting treatment.
I am aware, I mean, as we're going to hear in the next talk, of foam fractionation. There are several pump and treat methods that have been employed. Also, there's several sites in Australia that I know of where they're just scooping away the topsoil and setting it aside, trying to figure out what to do. So there have been several different remediation options that have been employed with PFAS remediation, all of them with varying degrees of success.
Thank you so much for that. Here's a question from the Arizona Department of Environmental Quality. Why did you create pulse input breakthrough curves rather than step input?
I'd be happy to discuss this question more offline, but we wanted to apply the same amount of PFAS to each of our soil columns, and so that was easiest done by using a pulse as opposed to a step or a constant application.
Fantastic, thank you. And this is another question from the Arizona Department of Environmental Quality. Do you have any insight regarding the conditions under which the micelles form?
So I think that there could be several different conditions under which the micelles form. One of the things that we did do is measure what we think of as the average critical micelle concentration for the AFFF that we used. And that value, because of the number of PFAS and the concentration of PFAS that were in that AFFF, was lower than any individual PFAS in the mixture. And so that being said, we knew there were micelles going in the top, but then in the actual subsurface, even if the AFFF was applied below the CMC, it is possible that these PFAS could be aggregating on soil surfaces or at the air-water interface. And because of that change in concentration, they could be forming hemimicelles or full micelles.
Thank you. And this is a question from the Air Force. Are lysimeter data effective in investigations of AFFF impacted soils based on your work?
I know that there's a significant effort going into improving lysimeter measurements or lysimeter approaches to measure PFAS in AFFF impacted soils. And I think the question really becomes, what PFAS are you interested in? In our experiments, we observed that anionic PFAS, so PFOS, PFOA, everyone's favorites, were much more mobile compared to the precursors, water ionic PFAS. And so if the PFAS aren't absorbing to the soil itself, then yes, a lysimeter could be an effective tool for characterizing the amount of PFAS in a system. But if you're not getting any leaching off of the soil, then a lysimeter isn't going to capture anything.
The questions are coming in so fast, it's hard to keep up, but I'm going to keep throwing them at you. The next one is from the North Carolina Department of Health and Human Services, and starts off with a statement about the soil carbon organic matter additions being used as a way to slow contamination. But in your experiment, there was not significant absorption to the organic horizon. So the question is, do you feel that carbon is not as much of a factor when it comes to PFAS absorption?
I think I'll give two initial responses to this question. One, it depends on what the quality of the organic carbons, the types of functional groups that are present, or what that organic carbon was derived from. That can play a huge role in PFAS absorption. But one of the other things that we observed is that PFAS do not want to be in the aqueous phase. And so they will find any surface that is not the aqueous phase, and whether they're actually interacting with that phase or whether they're just kind of being hydrophobically pinned to that phase is another question. So strictly using organic carbon and introducing that as a solid phase into an aqueous system could be a very effective remediation tool. It just depends on what PFAS that you're interested in, and if that PFAS is then actually interacting with the organic carbon surface through, for example, electrostatic interactions, or whether it's just being hydrophobically excluded from the aqueous phase.
Great, thank you. This is a question from the Washington Department of Ecology. You can answer it as briefly or as detailed as you'd like, but have you looked during your doctoral work on DNAPL and PFAS interactions? Or is this other work that Jennifer is doing that you're not involved with, Tom?
By and large, I have not been involved with the fuel work. For the fuel work or the NAPL work that I have been involved with, we have strictly looked at light non-aqueous phase liquids, so Jet A. I know there are a few papers that have come across where they've considered PFAS interactions with DNAPL, so the dense non-aqueous phase liquids, but my experience is strictly with LNAPLs.
Great, thank you. All right, two related questions from our audience having to do with environmental factors or co-contaminants or co-variables in the field. So have you looked at whether things like temperature or humidity or the presence of nitrate, nitrite, or other inorganic ions, have you looked at their impact on the ability of PFAS to sorb to soil surfaces?
We have not considered yet variations in, or temporal variations in soil moisture or temperature. We did address the variations in moisture to a degree with our unsaturated work, but we have not specifically considered the presence or absence of kind of what could be considered a background electrolyte, such as nitrate or nitrite in the system. There are potential mechanisms through which the PFAS can interact with those analytes or with those electrolytes, but we have not specifically investigated that yet.
Thank you. We have time for maybe 3 questions. So the next one is from the Florida International University. Have you looked at whether soil clays impact the KD values that you used, and did you measure the soil clay content?
We did measure the soil clay content. The soils in which we were working had very little clay. There was small variation in the different soil horizons that we used, but clay content overall was quite low. Again, clays can offer a significant phase in terms of just being a large amount of surface area, but they can also offer different electrostatic interaction possibilities. And again, it comes back to which type of PFAS are you interested in. If you're considering PFAS or PFOA or some of the anionic PFAS, at least in our research, we found that they were more interested in just getting out of the aqueous phase and partitioning to, or being hydrophobically excluded to any sort of phase. So adding more surface area from clay would increase at least temporary retention of analytes like PFAS and PFOA. Depending on the type of clay that you added and its electrostatic potential or the type of isomorphic substitution that it had undergone, it could offer different interaction potentials for zwitterionic precursors, zwitterionic PFAS that have a higher capacity to interact electrostatically with the soil system.
Thank you, Tom. One last question, and then we'll try and get back to you at the end of the webinar to answer any outstanding question. But this last question is from ASCA, from the Air Force. At sites with highly variable soils, like those in alluvial or fluvial areas, it seems like there is so much unpredictability. So much more research is needed to apply at the field scale. Based on your work, would you agree or offer a different perspective?
I would agree. At some of these sites, the soil profiles or the types of soil that are present can be highly variable or highly heterogeneous. One of the things that we attempted to do with actually both with our saturated model that we developed as well as the unsaturated model, was to use parameters that were somewhat generalizable or that could also be looked up from online databases such as the Natural Resource Conservation Society or the University of California, Davis. Both have extensive soil maps where you can find a lot of this information. So at least with this approach, you can get an idea of the retentive capacity of your system just using quote unquote basic soil data and basic PFAS parameter or PFAS molecule parameter information.
Wonderful. Thank you so much, Tom. We really appreciate your efforts. With these questions that were coming in at lightning speed, we're going to transition to our second speaker now, but again, we'll come back to you towards the end, so please don't go anywhere. All right, it is now my pleasure to introduce our second speaker, Dr. David Reynolds, who is a senior principal engineer with Geosyntac Consultants based in Australia. As a contaminated sites auditor in Western Australia and Queensland, Dave's work focuses on transitioning remediation concepts to practice, as well as the value of information in site assessment and remediation design. Dave is the co-inventor of electrokinetic oxidation approaches for remediation of heterogeneous and low permeability source zones, as well as the use of electromigration for in-situ desalination. He has previously served as a research director at the Center for Groundwater Research, a senior technical advisor at two other consulting companies, and a lecturer at the University of Western Australia. Dave received a bachelor's degree in geological engineering from the University of Waterloo in Canada, and his master's and doctoral degrees also in geological engineering from Queen's University. Dave, please proceed.
Thank you, Rula, and welcome to everyone listening in today. So I'm going to talk about a recently completed demonstration validation project that was funded by ESTCP, and specifically looking at removal of PFAS from source zones using what we've been calling the DFAS technology. So my slide's not changing.
We'll go ahead and advance the slides to you. Just please state the slide number, Dave.
All right, so on to slide 47. So I'm going to present what DFAS is. I'm then going to walk through 3 phases of this work: laboratory testing, field tracer testing, and then the actual field demonstration of this technology, and wind up with some summary and conclusions. And next slide. So what is DFAS? So DFAS is a combination in situ remediation platform, and it includes primarily foam fractionation. And I'll talk a little bit about foam fractionation in a bit. But part of foam fractionation also involves redox geochemical manipulation. In our case, we ended up combining foam fractionation with groundwater recirculation. And then there are other additional add-ons that could be envisioned. Bioremediation enhancement. For starters, we tend to be adding oxygen right away into the subsurface. There has been work out there looking at combining foam fractionation with in-situ chemical oxidation, primarily for precursor conversion, and VOC removal, and probably some other things. But the main central focus of DFAS is the use of foam fractionation in situ as opposed to ex situ. Next slide. So in a picture, this is what we do with DFAS and foam fractionation. Because of the nature of PFAS, when you add bubbles, when you add these air-water interfaces that we heard about a lot in the last talk, PFAS is preferentially likes hanging out at these interfaces and will be removed from the water column by the bubbles that you've added to it. So the picture here shows the simple lab setup, testing the site water simply by adding and blowing ambient air. So we're not talking about any special gases here into the bottom of the water column, resulting in this foaming. Next slide. So when we translate that out into the field, what we see here is a monitoring well. The green line's the ground surface, and the monitoring well has a couple of screens, an upper screen and a lower screen, and a diffuser placed into the bottom of the well that releases bubbles, and those bubbles rise up through the water column within the well. During that process, the PFAS are preferentially adhering to the surfaces of those bubbles and therefore rising to the top of the well itself. At the top of the well, we have an extraction device for removing that foam. And in an ideal world, as the bubbles rise and expand, you're creating upwards flow of the water in the well. So the treated water with lower PFAS concentrations rises up through the well and exits out through the screen at the top. And that process requires the recharge of water from the source zone, higher impacted PFAS, in through the bottom screen, and it becomes a circular process. Next slide. So a few things we're thinking about, what do we need at a site to employ DFAS? Well, high permeability is good in this case. We're thinking medium sand or better based on the pilot test that was done. Water table close to surface, that's not a hard and fast requirement, but it certainly makes the foam extraction easier out of the wells. High concentration of PFAS. It's a bit of a brute force technology. The higher concentration of PFAS in the water, the more effective and the more mass you get out. Homogeneous porous media. Heterogeneity will cause problems, mostly with the recirculation, and I'll talk about that in a minute. And stable hydraulics. Large water table elevation changes can impact the efficiency of the system. Next slide. So quick snapshot. We started all this off with treatability testing as phase one. And so the site groundwater composition is the top right table. Concentrations, and we just listed 4 analytes there in the hundreds of micrograms per liter. And the results in the graph on the left-hand slide for 4 different compounds and based on percent removal. So if we start with the green line, which is PFAS, along the x-axis foaming time. So within 1 minute, it's greater than 90% removed, and it stays fairly constant. We see increasing performance in terms of percent removal with some of the other compounds. PFHXS was about 60% at 1 minute, ended up over 80%. Bottom right table shows the mass balance. We looked at the PFAS present in the water and then the PFAS that was extracted in the foam. And we pretty consistently found that there was more PFAS in the foam than was originally in the water. Some of that may be due to the difficulties of laboratory analysis of high concentration foams. There could be precursor transformations or other things, but take-home message was yes, the concept worked on the site water. Next slide. So we moved on to tracer testing, and the tracer testing component in the field was to confirm that our original design that we were going to employ was going to work at this site. A lot of the design work had been done conceptually before we got to a site selection. And the geology gremlins jumped up pretty quick again at this site. So we see in the figure here that we had 1 borehole log to work off of previously at the site. When we went out and we started doing the baseline background sampling, we found that there was a fairly extensive clay layer in the subsurface that was located at the same vertical elevation as that upper screen, and likely therefore prevent treated water flowing out of that screen and prevent the recirculation. So next slide, please. When we went out in the field to do a tracer test, we installed the TW6, which is an operational well, and then a number of upper and lower monitoring screens, the MWTs you see here. Fairly tight spacing. 5 foot is the largest radius of influence of the infrastructure, and we're planning on using 3 different tracers. Next slide. The tracer test, 3 different tracers. The first one, we'd installed a mini screen into the sand pack in the treatment well itself, which was labeled there with tracer number 1 release. The idea being that if we're releasing tracer into the sand pack around the upper screen, if you get this recycling, or if you get treated water flowing out of that upper screen, it's going to carry it back out into the formation. We should be able to see it in the upper and lower screens in the various monitoring wells. Tracer 2 is planned to be released just into the closest lower monitoring well, and tracer 3 into the furthest away lower monitoring wells. Next slide. And as we expected, based on what we'd seen in the geology and that clay layer shallow, we look at some results here. These 3 spikes on the graph are the signal strength from the fluorometers. So they're indicating the presence of tracer at 3 different locations. The A wells are the shallow, the B wells are deep. And yes, we saw tracer appear in the upper monitoring wells relatively rapidly close, and then less of a signal and later signal further away. And we did not see the recirculation. We did not see tracer appear at any of the B horizon or lower screened wells. So this caused us to go back to the drawing board and redesign the system a little bit. So next slide. And we ended up with a design that looks something like this. So we have 2 treatment wells, and treatment wells are the wells that we're injecting the air into, labeled TW1 and TW2 here. And then paired or coupled with those were 2 recirculation wells, labeled RW1 and RW2. And the concept is that we're pulling the treated water out manually out of the top of the TWs with the pump and putting it back into the recirculation wells to create this dipole. The orange colored circles here are the monitoring structure that we had at the site. Next slide. So quickly, some pictures. This is what the site looks like. In the left hand, you can see the 4 wells with the PVC stick-ups. Those are our treatment and our recycling wells and some infrastructure. The flush mounts are the monitoring wells. The picture on the right shows the control trailer. The thing I like a lot about this technology is from an engineering standpoint, it's not very complex. The entire control system is contained in that small trailer there. Next slide. And a little bit of some action shots. So what we see here on the left is the DFAS system in action. The gray pipe you see here is taking the foam from the wellhead and transferring it to the storage vessel at the end. And we can see the foam in this jar, this dropout jar, is accumulating quite rapidly. If you then take that foam and put it in a bucket or a vial and let it sit for a while, which is the picture on the right, you can see that foam eventually collapses. And what you end up with is a highly concentrated PFAS liquid that then has to go for disposal. Next slide. So what kind of performance are we getting with a single pass through the well? So the numbers on the left are the background formation concentrations in the hundreds of micrograms per liter. Formation water in, treated water out, roughly in most cases an order of magnitude reduction. We saw less reduction in PFH excess in the field with a single pass, very similar to what we saw in the lab. And next slide. And then what does the foam that's coming out look like? The picture up on the top there is that's the holding tank at the end that the foam was pumped into. And concentrations somewhere between 500 and 1,000 concentration factors. So we're going from hundreds of micrograms per liter up to tens or hundreds of thousands of micrograms per liter in the foam. Mass removal in the first tank, which is the table on the bottom left there, is we're getting significant mass removal out of these two wells over the course of the first half of the trial. Next slide, please. So now we'll go on to some results, some in situ results. And for each of the graphs I'm going to show you, there's a little key up in the top right here. The treatment wells are blue, the recirculation wells are green, and we're going to look at one monitoring well at a time. And this is MW105, which was located right in the middle of the treatment zone. The x-axis on the graph are the groundwater monitoring events, so it's not a perfectly linear scale. We're just looking at snapshots in time, roughly a month apart. So we look in the middle, very good performance as you'd expect. The dark blue line, which is PFAS, started in the 1,100 micrograms per liter, had dropped to roughly 20% of that within the first few weeks of operation, and then down into that 90–95% treatment range across the total duration of operation. Next slide. So now let's look at a monitoring well outside of the footprint. So 104, which is to the left here. Again, similar behavior, a little bit slower and a little bit less overall reduction. PFAS started off at 700 over the course of the DEMVAL, got down to about 100. Next slide, please. MW106, so we're now on the other side of the treatment cell, the same range, the same distance as MW104. Again, very similar type behavior, slower than we saw in the middle of the treatment cell as we would expect. In this case, reaching an asymptote when we started to see some increase in concentrations again by the end. Next slide. So now we're going, let's even further outside of the treatment cell on the left. So this is about 10 feet outside, and I think we can safely say that we're outside the radius of influence of the treatment system with this one. Next slide. So if I plotted these up rather than just graphs, let's stand back and let's look at the footprint of the treatment. What we have here is the ratio of the PFAS at a given monitoring event divided by the original PFAS concentration in the well. And in this case, 0.1 equals 90% reduction. GME 1, 3, and 5, this one's just for PFAS. We focus on the right-hand graph, groundwater monitoring event number 5. You can see the bright yellow area in the middle, which is the 90% reduction area, has pretty much encompassed the treatment cell itself, and it drops off. And if you look on the far left side, that was where we saw the data from the monitoring well that was outside of the radius of influence. Next slide. Similar graph for PFOA, not the extent of removal or reduction that we saw for PFAS. But again, seeing reduction, this time it was on the order of the 90% was a much smaller footprint. The treatment cell itself, the treatment area, was somewhere around 80%. Next slide. So let's leave groundwater now and let's go to soil. We took soil cores during the installation of the monitoring wells and had them analyzed. And following the demonstration, we went back in and took soil cores as close to the location as we could. There's a well in there now, so it obviously wasn't the same location. So let's start right in the middle of the treatment cell with MW105 again. The table on the right here is the percent reduction of PFAS, PFOA, and the sum of PFAS at various depths in the soil profile. And just as a reminder, in the bottom right was the percent reduction in water achieved at that monitoring well. So we see in the vicinity, in the range of 60 to 80%. percent reduction, with the exception of the shallowest sample, which is the 8 to 9 feet, which is below the water table, but at the bottom of that clay zone, where in this well, we actually saw an increase in PFAS concentration. Next slide. Moving outside of the left, so we're following the same pattern I did with the groundwater. Again, 70, 60, 80% in the deeper area, but again, we saw this increase in concentration in the shallow soil interval. And next slide. Now we've gone up gradient, so I didn't present this groundwater data, but it was similar to the others, and it was within the radius of influence, ignoring the -138 there for the time being. That the concentrations now, the percent reductions were similar to what we saw, if not better, within some of the wells, but now we did not see this concentration or increase in concentration of either PFAS or PFOA. Next slide. And one more, top right, lower removals, 10 to 20% now. And we also saw concentration at a little bit of a deeper depth than we did in the other ones. So on to the next slide. So let's just do an initial mass balance here. And we just looked at the central volume, which is the treatment area, a little bit outside within what we knew was the radius of influence of the system. It's about 20 feet by 10 feet. And then vertically, which is the upper red box there. And then vertically, we looked at the interval between 10 feet and 17 feet. So deliberately excluded the 8 to 9 foot concentrations. And I'll talk about why we did that and what that means in a bit. If we average all of the soil concentrations baseline and post GME5, which is when the system was shut down, we get about, soil volumes about 40 cubic meters. And if we do the math, we come up with about 19 grams of PFAS, so not total PFAS, just PFAS removed from this system. Next slide. And if we then look at, we all, of course, had all of the effluent analyzed that was in the tank at various times. Over the course of the DEMVAL, we removed 47 grams of PFAS. So more than we would have thought from the soil. And this was good to see that when we started seeing this concentration effect in the shallow areas, we wanted to make sure that we were not just moving PFAS around in the subsurface with this process. We certainly were doing that, but we were also removing a fair amount of mass. Next slide. So if we look in cross-section, just looking at those percent reductions, we've kind of broken them out into different boxes here. That middle well is the treatment well. At depth along the screen of the treatment well, we consistently saw greater than, oh, there's a pop-up. Consistently saw greater than 80% removal. Outside of the immediate area of the treatment well, at depth, somewhere between 60 and 80% removal based off the soils. Shallow at the treatment well itself, we saw 60 to 80% removal. It was only out at the fringes in the shallowest soil samples where we saw this concentration effect. And it's not surprising, we're putting bubbles in, we're creating buoyancy effects, we are pushing water out of the top of that well to a minor extent here, as well as recycling it. But overall, the process removed mass did not just redistribute mass. Next slide. So what did we learn? Groundwater concentration reductions in the 80 to 96% range within the radius of influence or the treatment footprint. Similar numbers in soil, a little bit less percent reduction. The system operated very well. By the time we got to GME4, 95% uptime. Overall, 107 grams total PFAS now removed from this source zone in 12 weeks with 2 wells. effectively simply by blowing air into the wells and relying on the surface chemistry and the surface physics of PFAS. And then we also had the condensate, so that's what we saw in the little bucket in the big tank, sent off to Colorado School of Mines as part of another ESTCP project to demonstrate that this high concentration liquid could be effectively destroyed, in this case by hydrothermal approaches. Next slide. So benefits to DoD. I think we've demonstrated that DFAS is a promising technology for PFAS removal. It is a very robust technology that does not have a pile of complex engineering or geochemical manipulations involved with it. It's flexible. We learned that on the site. I talked about water table elevations earlier, and we had some significant water table elevation changes over the course of this project. It should be considered a mass removal technology, and with that, I mean, it's not likely to achieve future target levels, which are anticipated to be very low in drinking water. We saw we were getting 90% removal, but the technology at the present time, and it may in future iterations be able to get down there, but we're looking at it now as a low-cost, robust mass removal technology. Next slide. The team, it wasn't just me or Geosyntec, Chris Nelson at E-, big part of this, doing the design work and the field work and all of the hard yards in the field with Rich Spiar from BLDI. The Navy team of Tony, Jason, and Jillian have been a great help during all of this, and Will Caldecott from Isotech, who has been there with us from the beginning on this journey. Next slide. And my contact information is there on the screen, and I will be, after taking questions in the Q&A, obviously, but happy to have any questions fired my way afterwards.
Wonderful. Thank you, Dave. Just a question related to the link to your project webpage. When do you guys expect to upload the final report? When will it be available for our audience members to download?
The current schedule is the draft report should be done and then submitted to ESTCP in early September. So there'll be a delay, of course, while it goes through final, but hopefully by the end of the year.
All right, excellent. So we have a bunch of questions that have come in for you, and depending on how we do, we'll pull in Tom back into the discussion. This first question is from the Alabama Department of Environmental Management. Could your system be used at a landfill with an EPA Subtitle D style liner, especially since those sites require continued groundwater monitoring?
Without thinking about it too much, I would say probably. If you can create, a mechanism where you can get bubbles into the zone you want to treat, and then they can be allowed to rise to the surface, then the configuration or the porous media that you're using shouldn't matter very much.
Thank you, Dave. This next question is from the University of Florida. Can your system be modified to address a vadose zone source?
We have been talking about this in the writing of the report. Short answer I have is I'm not sure. We haven't tested that. I think it would be less effective off the top of my head, but the physics are still pretty much the same. So short answer, yes, I think you could. Would it be as effective? Don't know.
Wonderful, thank you. This next question has to do with whether your demonstration site contained non-fluorinated surfactants, source from AFFF, for example, that could have helped with the foam fractionation? Did you look into that?
We did preliminary when we got site water. We did preliminary analysis of that site water. I can't remember off the top of my head if they were present. Now, there's a big body of science out there that, yes, you can improve the performance of foam fractionation by adding other surfactants. That wasn't part of the scope of this DEMVAL. I know it's being looked at in other ESTCP projects, but there's no reason the system could not be modified to include non-fluorinated surfactants to increase the overall effectiveness of the process.
Well, you just answered the second question that came in related to adding benign surfactants to help achieve PFAS removal goals. So thank you for that. All right, here is a question from the North Carolina Department of Health and Human Services. They just want to confirm that there were no chemical additions, just ambient air. So can you please confirm that and recommend improvements in the technology that could be implemented, especially around in areas of contamination surrounding drinking water wells? If we're talking about lower concentrations, is it even applicable in these types of situations, or can you recommend next steps and improvements?
Right. So yes, I can confirm there were no chemical additions whatsoever. This is simply ambient air run through a compressor and pumped into the well. So with that, there are a number of ways that this could be improved. So when we looked at this in the lab, bubble size is something we looked at. There should be a relationship between removal efficiency and bubble size, right? Or the radius of curvature of those interfaces. We found that within the range of bubbles we were looking at, the size range, it wasn't that important. So most of the literature says when you're pushing down to really small bubble sizes, that's where you start to get the kick, but that increases the complexity and a number of other issues. So bubble size is one thing that could be looked at to increase the removal. Other gases other than ambient air. So there's also been a body of work out there looking at, using nitrogen, for instance, that will increase performance. I couldn't tell you how much that would increase performance in the field in a situation like this. But yes, there are other improvements that could be done and should be looked at in the future to improve the overall process. Whether it's ever going to get down to drinking water, I think we're a long way from that, but it's not impossible.
All right, thank you, Dave. And a related question from NAFBAC Southeast. I think it was touched upon in the previous question, but can you propose with a straight face this technology to address low-level PFAS impacts in groundwater? Is there a threshold PFAS concentration necessary for adequate foam generation?
Again, the short answer here is yes, there's going to be a threshold. I think the key word in that question is adequate. That one of the interesting things we found is not only the PFAS concentration, but the PFAS mass feed into the well. So with the system we had set up, it was a very, very low flow, that recirculation. I didn't go into details about it, but we're talking less than a gallon per minute. So we were doing that with a peristaltic pump, and as you increase the pump rate, it had a direct bearing on the amount of foaming. So as you're increasing the pumping rate, you're increasing the recirculation through that treatment well, and the more water you're adding in, the more foam you generate. So that's one operational fine-tuning aspect that you can look at.
Thank you, Dave. This is a question from AECOM. How much water was removed and was the water discharged with standard permit approvals? What did you do with the water, if any?
Yeah, so all of the foam water that was removed went into that big 1,100 gallon tank that you saw in one of the pictures, and then everything other than the samples taken for analysis that was in that tank were disposed of through regular waste disposal practices.
Wonderful. This has come up in several of the questions that are coming in terms of the effectiveness on the process on a broader range of PFAS. So specifically, one of the questions relates to shorter chain compounds like PFAS. Have you looked at that? And what can you share?
Yes, it's a very good question. The process is highly effective on the longer chain ones. As chain length reduces down, the PFBSs, that kind of range, the process is less effective. And that's not something we looked at with this preliminary study, but what I would do is point the reader or the questioner or anyone that's interested to look at the In-Situ Foam Fractionation work, where they've spent a lot of time and effort on focusing on those shorter chain PFAS compounds to be able to remove them. So the foam fractionation can do it. It requires a little more engineering. It requires a little more finesse. We haven't got there in situ yet.
Excellent. All right. A lot of questions about the foam that is being generated, how that is being treated, and whether you're considering DFAS demonstration in line with a destructive technology at the tail end. So 3 questions there from different audience members, one from Purdue. So can you please give us an idea about next steps and foam disposal?
Right. So for the demonstration, as I said, we just did exactly the same you would do with PFAS impacted water that needed disposal. So nothing researchery or nothing advanced, but it would be very elegant to have a system, an on-site system, and whether it's one of the myriad of technologies that ESTCP is looking at now with plasma or e-beam or whatever they are, coupled directly to this system, so you're creating zero waste and no need to dispose of it. The other factor that goes hand in hand with that to a certain extent is we want to make this foam as concentrated as possible to reduce the volume that requires treatment. And we were seeing 500 to 1,000 times concentration factors in this. I think we can do much better than that. But this was the first kick at the can. If we could get to 10,000, then I think we'd really be in the sweet spot of this technology to minimize foam generation, and coupling that with an on-site destructive technology would be a very nice system.
Wonderful. Questions are still coming in. I would like to encourage our audience members to reach out to Tom and to Dave using the contact information provided here. Before we wrap up, one more question for Dave, and then I'm going to let Tom and Dave discuss any last takeaway messages. But this is a question from the Navy, Dave. Can this process be adapted for surface water intakes, things like lake or ocean water? Are there any above ground units for for water streams that you're aware of?
Again, the physics of the process should work perfectly well in surface water applications. We haven't done it in surface water. There are other ESTCP projects that are looking at different configurations of foam fractionation that haven't got to the field yet, but conceptually, and one of the benefits with doing it in surface water is you don't have the geology gremlins. So you're dealing with a much more homogeneous system to try and treat.
Wonderful. So a much simpler way to implement the technology. Great. Well, again, our apologies for any outstanding questions. In the next few minutes, I'm going to ask Dave and Tom to just please discuss next steps or any last messages you want to leave with the audience before we conclude. So Dave, let's just start with you and then turn it over to Tom before we wrap up. Anything you'd like to add? Or have we exhausted you with questions?
There's been some really good questions and a lot of them. One thing I'm going to be interested in doing is looking at Tom's presentation in detail and how that could possibly impact our next attempt at this. Because one of the other things we've thought about in terms of mass removal is if we are altering the geochemistry, right? We're injecting air, we're injecting oxygen. Is that releasing, and I'm using the wrong terms here after everything I learned from the last presentation, is that releasing bound PFAS into the system? So not only is it just removing it, but is the process of doing this resulting in more available PFAS to the bubbles? So that's kind of what I've been thinking about for the last hour and a half.
Wonderful. We love to see collaboration between different researchers, especially between SERDP and ESTCP projects. So thank you for that, Dave. And Tom, I apologize that we weren't able to get to any additional questions for you and for Jennifer, but is there anything you'd like to leave our audience with before we wrap up?
Yeah, similar to Dave, just want to say thank you for all of the very insightful and interesting questions. And I was really appreciative of Dave's talk. And one of the things that really just struck me and they're taking away from this is that this issue of PFAS and PFAS source zones, either if you're focusing on the contamination end or on the remediation end, that it seems to be a more complicated question and solution than at least I was expecting from the get-go. And then one of the things from the research that I've been involved with, specifically thinking on the broader scale, is that with these soils that are impacted by PFAS, specifically thinking of kind of the classic PFAS that people like to talk about, so the PFAS, PFOA, at least in these low organic matter systems, we may see increased leaching of PFAS, PFOA into the groundwater as the system moves through wet and dry cycles, just because it seems that these types of PFAS aren't interacting very specifically with the media itself. And so that may play into remediation techniques or different monitoring approaches.
Thank you. And again, thank you both for a fantastic webinar. We're going to go ahead and wrap up. Before we do that, I'd like to remind you that the next webinar in the SERDP and ESTCP webinar series is on Thursday, August 25, on DoD-funded research efforts to build upon hydrologic modeling elements necessary for strengthening DoD installation water resilience. This webinar will feature 4 speakers from national labs and the DoD, the Air Force. A registration is open, so please visit the webinar webpage to register for this and other webinars through early 2023. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you very much.